Welcome to Plutus IAS, and today we are covering the use of LTA, which is also goes by the name of lead tetraacetate or PBOAC whole 4. Now we have seen that LTA is mostly promoted as an oxidizing agent, but apart from oxidizing agent, it has more purposes. For example, it is used in cyclization towards the formation of your alkenes, lactones, and other important compounds. And it is also used for acetyling and methylating agent. And today we are focusing on that particular one. See, the use of LTA from apart from the oxidizing agent, these properties come under the category where LTA is being utilized for addition of other for your substitution of other groups in the compound. So for example, if I need to give you an example, see, the first case comes out to be, let's suppose we have a cycloalkene, and whatever the example that I'm writing, they are applicable towards your any kind of alkene. But for the current example, I am focusing myself on cycloalkenes. Okay, and this property, let me rewrite it again, that this property is applicable to, it is applicable on cycloalkenes, cycloalkenes, and also on your carbonyl compounds, carbonyl compounds. Okay, for example, if I give you a carbonyl compound first, for example, let's say this is the compound CH3, C double bond O, CH2, C O M E, OMe. So here we can see this is an ester. On use of LTA, if you use LTA here, this alpha carbon with the most acidic hydrogen will get substituted. One of the hydrogen will get substituted and will get acetylated compounds. This is the same case. You can also go for, let's say, acetone. If we are given CH3, CO, CH3, on using LTA, a similar phenomena will be obtained, and in this case we'll get a ester, CH3CO, it will become CH2OAC. Now, but what if I'm using a cycloalkene? In case of a cycloalkene, let's say for this case, let's say this is a cycloalkene and I'm taking LTA. Now the problem is, on using cycloalkenes, the LTA will give us numerous number of compounds. For example, the major product that in the reaction that will be found includes allylic methyl, dimethyl cyclohexane, one with syn addition and other as NT. Now, other products include allylic acyl group, diacetyl cyclohexane, and other one includes now keep in mind that the number of products that I have written, the number of product can also further get increased if you include if you are including a more number of the byproduct. For example, methane will also be obtained, ACOHR will also, the reagent will also be there. So in such scenario, these are the most major products that we have. So here, by the reaction, I see that there are two sets of compounds that I am getting. First, it is your allylic methyl group. Why? Allylic methylation, where we have done methylation, and the second one where I am having acetylation. So now the question arises, what is the mechanism that is being followed behind the reaction? So let's say this is the mechanism. Now, the mechanism for this reaction proceeds via free radical mechanism. Free radical mechanism. But if you have already studied about reagent, you already know that the oxidizing properties of LTA are always studied in terms of your ionic mechanism. But for this specific case, for the substitution group, substitution reaction using LTA, we are using free radical mechanism, and this will be followed as this will be followed as we'll have PbOAC OAC whole twice, one OAC right here, second OAC right here, homolytic fission, and this is, and what this gives us, OAC radicals 2 moles and 1 mole of lead diacetate. Now the possibility that goes, now we'll have two possibilities if you are going for allylic, if you are going for acetylation. For acetylation, the reagent that will be progressing, the intermediate that is progressing the reaction would be the OAC radical. But if you are going for methylation, the reagent that will be responsible for the forwarding of the reaction will be CH3 C double bond O radical. Now this radical will undergo homolytic fission and remove CO2, forming the CH3 radical, which is responsible for the methylation. So both the intermediates are being produced by the intermediates. Now since free radicals are involved, like I said, more number of product can be obtained from the reaction. For example, CH3 can combine with itself, it can combine with OAC, okay, it can form methane, hydrogen abstraction, multiple products can be there. But we'll be focusing ourselves only with these two sets of the products that we are getting. So for the next case, if I'm talking for for the next case, let's say I'm talking first for acetylation. Acetylation. Now, the first possibility is that I can use the OAC radical and the homolytic fission occurs at the alpha hydrogen, which will be attacked by OAC, removing the first mole of ACOH, whereas the second mole of OAC that you have produced, if you see here, we have produced 2 moles of OAC. The second mole of OAC radical will attack this position, and this will gives us our acetyl product. Next, the second option comes if this pi bond undergoes homolytic fission and the 2 moles of AOC that we are taking, they react these two places, giving us OAC here, and the second one will be getting here, one at wedge and the second at dash. Okay, so I hope this part have been completely clear to you. Now for the second case, what if I'm talking about methylation? Now methylation will follow exactly same process. The only problem that was that the formation of intermediate that is progressing the reaction, and we have already learned how to produce the intermediate. So now we have intermediate, we'll go by the again exactly same phenomena as we have followed with the acetyl case. Alpha hydrogen first option, we have taken CSC radical. Now The hydrogen will be taken, the one byproduct we'll have is CH4, and the second CH3 radical will attack this position, giving us the compound allylic methyl. Similarly, just like the previous case, the pi bond can also undergo homolytic fission, giving and 2 moles of CH3 radical. One methyl at wedge and the second one at dash. So now we have seen that this reaction is non-stereospecific in nature because we are getting multiple products, and that too some of the products when we are not actually listed in the reaction. So that means a number of byproducts, a number of major products, these products will exist all together simultaneously. Since majority of these groups have nearly same properties, they are not soluble, hence their separation is very much difficult. So we have seen that as a substitution agent, LTA is very bad, but its properties can be enhanced if we are using certain kind of reagent. For example, if you heat it with ACU, if you are using acetic anhydride, in such a case the reaction can be stopped at the acetyl process. Methylation will be suppressed, and that is because the use of acetic anhydride enhances the, it is a viscous liquid. So in the, since the solvent viscosity gets increased, the radical the sorry as the viscosity of the radical gets increased, the attack of the CSC radical gets suppressed. Okay, so I hope now you have the any of your doubts regarding LTA now being corrected, and the how's the substitution of the reagent will occur. Okay, in case of any doubts or any specific topic that you want us to make the video, you can add up it to the comment section and we'll look forward to it. Thank you for joining us.